Okay, good. So let's start writing down what these Feynman diagrams are equal to. Okay, let's look at this first diagram. Good. Uh, so the line just going from x1 to x2, well, this is going to be g of x1 comma x2. That's the rule for the line. And let me just remind you, what is g of x1 comma x2? Well, it's an integral before p over 2 pi to the 4. So this is something that you really need to remember. I over p squared minus m squared plus I epsilon. And then we'll have an e to the I p dot x1 minus x2. So we've got Feynman's I epsilon prescription here. So don't forget that. And also don't forget that by p squared here, we mean p naught squared minus p dot p. Okay, that's the Green's function. Good. Okay, now let's take a look at this Feynman diagram. And I want to write it down and manipulate it a little bit. So let's see what we've got. What is this equal to? Well, let's first of all, so what do we have? Well, we will have minus 24ig for the vertex and an integral d4x. Then what are the lines? Well, we've got a line going from x1 to x. The loop is a line going from x back to x. And then the final line goes from x to x2. And then the only other thing we need to remember is that there's one closed line. So we need to divide by 2. Okay, so let's keep going. So this is minus 12 ig integral d4x g of x1 comma x g of x comma x g of x comma x2. Now, what I'd like to do next is to perform the integral over x. So to do the integral over x, I actually need to plug in what are the values of these Green's function. What's the explicit expression? So this will be equal to minus 12 ig. Then there is an integral d4x. We have got a g of x1 comma x. So we'll need an integral d4 p1 over 2 pi to the 4. I've called it p1 because we're going to need momentum for each line. So let's start with p1, p2, p3. Then we've got I over p1 squared minus m squared plus I epsilon. And the exponential is e to the I p1 dot x1 minus x. Good. Then for the g of x comma x, let's write integral d4p over 2 pi to the 4. We'll have an I over, so we'll make this p2, p2 squared minus m squared plus I epsilon. And then we've got the g of x2 comma x. So times by an integral d4 p3 over 2 pi to the 4 e to the I p3 dot x minus x2 over, there should be an I, and over p3 squared minus m squared plus I epsilon. So each of these factors is for one of these Green's functions. So I'm just going to underline the terms in a certain color so that you can see the correspondence. Okay, so I've indicated the expression for each Green's function. And in fact, I could even indicate it here on the diagram too. So this is now even indicating it on the diagram. Good. Okay, good. Now, I want to do the integral over x. So let's write this as minus 12 ig integral d4 p1 over 2 pi to the 4, and integral d4 p2 over 2 pi to the 4 and an integral d4 p3 over 2 pi to the 4. Oh, one thing that I should have stressed, but didn't, look at the integral d4 p2, the blue Green's function, okay, the one underlined in blue. There was no exponential factor. And the reason for that, well, I could have put in the exponential factor, but it would have been an e to the I p2 into x minus x. X minus x vanishes, and e to the naught is just 1. So I didn't put in the exponential. Okay, so good. Okay, then what do we have? So I'm going to push all of the x dependents to the end. Okay, so we've got an I over p1 squared minus m squared plus I epsilon. We'll have an I over p2 squared minus m squared plus I epsilon. And then we've got an I over p3 squared minus m squared plus I epsilon. Then we've got an e to the I p1 dot x1 minus I p3 dot x2. And now comes the x dependence. We've got an integral d4x e to the I x dotted into, and now we've got p3 minus p1. So take a look at this. If we wanted to indicate the momenta on this diagram, so let's maybe indicate that. This first line, the red line, this had a momentum of p1. That green line, well, that had a momentum of p3, and the blue line had a momentum of p2. Okay, so that's a good thing to bear in mind, and we'll come back to that in a moment. Very good. I might want to draw a little bit, so let me put in a little bit of space here. Good. Okay, good. Now we can now perform this integral d4x e to the I x p3 minus p1. So this is an integral that I've told you is very important and is going to feature a lot. There's a 2 pi to the 4, and there's a delta 4 p3 minus p1. So what does this delta function do? It sets p3 equal to p1. Okay, so we can actually do the integral over p3. So let's do the integral over p3. Then we will have minus 12 ig, an integral, we'll still have p1, so d4 p1 over 2 pi to the 4. We'll have an integral d4 p2 over 2 pi to the 4. We no longer have the integral d4 p3 because we're going to integrate over d4 p3, which is going to set p3 equal to p1. The 1 over 2 pi to the 4 with the d4 p3 will cancel with this yellow 2 pi to the 4. So the 2 pi's nicely cancel. And the I over p1 squared minus m squared plus I epsilon times the I over p3 squared minus m squared minus I epsilon becomes I over p1 squared minus m squared plus I epsilon squared. Because now p1 is set equal to p3, we've still got I over p2 squared minus m squared plus I epsilon, and then it is multiplied by e to the I, and now p1 is set equal to p3. p3 is set equal to p1, so we've got e to the I p1 x1 minus x2. Good, and we've done the integral over x. We will keep going with this in a moment.